So hi and hello. Welcome to our channel named Algo Exploration. My name is Samir and today we will be going to learn about quicksort. Actually, explaining quicksort in detail will be very lengthy lecture, so I'll be making the lectures in parts. So this is the first part. Okay, now let's get started. In the previous lecture, I have shown you how the merge sort and the bubble sort works. Let's have a look at its time complexity. Again, bubble sort at worst case will take order of n square time. Average case will also take order of n square. But for the best case, it will take order of n. Okay. What about the merge sort? At worst case, it will be order of n log n. Average case will also be n log n. And best case will also be order of n log n. Remember this part because further we'll be needing it. Now, before going to the actual quicksort, let me build some intuition that how the quicksort will work. So this is the first question, that we have given an unsorted array of size n in which we have to return that array only, whereas the first element should be in its correct position. Let me explain it more clearly. Consider the first element as a of 0 as pivot, okay, such that if a of I is less than or equals to pivot, then in the resultant array a of I should be residing on the left side of the pivot, okay, or else if a of I is greater than pivot, then in the resultant array a of I should be on its right side of pivot. Okay, now let's take an example and see. We have given an array in which the element 4, 7, 1, 2, 5, 3 and 6. Now the first element will be act as a pivot, and now we have to rearrange the element such that the first element, that is 4, should be on its correct position. So 1, 2, 3, 4, 7, 5 and 6. Now 1, 2, 3 are smaller than 4, so it will be residing on the left side, and 7, 5 and 6 are greater than 4, so it will be on its right side of. So the order of the elements which are on the left and right will not matter. It may be in a sorted manner or it may not be in a sorted manner. Our concern is we only want an array in which the first element should be at its correct position. So what will be the first approach to get the solution? The first approach is we have to sort it. You can use bubble sort or merge sort. But bubble sort will take order of n square time and merge sort will take order of n log n. If we sort it, let's say we take this array only, the resultant array will look like this: 1, 2, 3, 4, 5, 6 and 7. So the first element, that is 4, will be at its correct position. Okay, so we have seen the time complexity, that the efficient will be n log n. Now can we reduce it? Yes, we can. So what will be the approach? The second approach will be, we will take the help of two pointer technique. So the first pointer will be I, in which it will take care of all the elements which are smaller than or equals to pivot. Let me explain how. Observe here carefully. Let's say we have an array of size n. The indexes will be from 0 till n minus 1, right? 1, 2 and so on. Now let's say the pointer I is at this position. So the elements from 0 to I will be always lesser than or equals to pivot. Here order will not matter, and the elements from I plus 1 till last index will be always greater than pivot. Now observe here, actually I will act as a boundary in which the elements will be lesser than pivot. So remember this case. Now the second pointer will be j. We need j because actually we need to iterate from 0 to n, right? So it is nothing but iteration from start to end. Let me take same example and show you. Let's say we have an array. Elements are 4, 7, 1, 2, 5, 3 and 6. So pivot will be our first element, I will be at first only, and j will be at I plus 1 because we need to compare, right? Now as I said that I will act as a boundary in which elements from 0 to I will be lesser than pivot. Okay, now we will check whether a of j is lesser than pivot, lesser than equals to pivot. So this will be our condition. So j is at index 1, so 7 is less than equals to pivot. No, it's not. We will not do anything, we will simply increment j. We will take action only when this condition satisfies. Now here 1 is less than equals to 4, yes it is. Now we will take action here. As I said that I will act as a boundary in which the elements will be smaller, right? So 1 should be inside the boundary of I, right? So we will increase our boundary by incrementing the I, and we will swap these two elements, a of I and a of j. So 1 will be here and 7 will be here, and again we will increment the j as well. Now again we will check whether a of j is less than equals to pivot, that is 2 is less than equals to pivot, yes it is. So again we will increase our boundary and we will swap a of I with a of j. So 2 will come here and 7 will come here. Now we can see that from 0 to I all the elements are smaller or equal to pivot, that is 4, and we will again increment the j as well. At every iteration we are actually incrementing the j. Now we will again check whether a of j, that is 5, is less than equals to pivot. No it's not. Then simply increment the j. Again we will check, is 3 is less than equals to 4, yes it is. So we will increase our boundary by incrementing the I, and we will swap a of I with a of j. So 3 will come here and 7 will go here. Now again increment the j as well, right? Now again we will check whether 6 is less than equals to 4. No it's not. So we will increment the j. Now actually j is out of bound, so we can see that from 0 to I elements are lesser than equals to 4, but 4 is still not at its correct position. We know the boundary where the 4 should lie. The 4 should lie here. Due to this, the element except 4 should be on the left side of 4. So we will simply swap. 4 will come here and 3 will go there. Now we can see that 4 is at its correct position. So actually using this algorithm we will get our solution. So let's see the pseudocode here. Now I have named this algorithm as partition, passing the array A, and pivot will be a of 0. I will be initialized as 0, and j will be running from I plus 1 till n. Here n is nothing but the length of an array. Now using the for loop we will actually iterate and see whether a of j with some condition and pivot. What will be this condition? We are taking action only when a of j is actually lesser than or equals to pivot, right? So this will be lesser than or equals to pivot. If this condition satisfies, then we will increment the I, that is increasing our boundary by 1, and we will swap a of I with a of j, right? And after the loop we will actually swap a of I with pivot, right? So this is our code. So what will be the time complexity here? We can see that the for loop is running from I plus 1 till n, that is nothing but n. This will be constant and this will be also constant, right? So time complexity will be order of n. And what about space complexity? It will be order of 1 because we are taking no extra space. So this is actually the partition algorithm. Now in the next lecture we will be continuing about the quick sort again. So thank you.